I'm moderating this session on the analytics to support bus operations. Sorry, let me just close these things. There we go. Okay, so we've got three presenters. The first presenter is Wang, who's been working on a project I'm really been very keen on, but he's going to talk about a somewhat different topic today. But Jiahao is a PhD candidate in the Department of Civil and Mineral Engineering. His research focuses on the application of deep learning and reinforcement learning techniques, aiming to create a more human-involved and intelligent expert system that enhances traditional transit control processes, in particular real-time operational control. Fun fact, when Jiahao isn't doing research, you'll likely find him cycling on the Great Bike Trail in Toronto. Cycling has become his newfound passion, allowing him to improve his fitness and explore the beauty of the city. This time we're going to do like Amber did. We'll run the presentations and then save time for questions at the end. Jiahao, turn it over.
Hey guys, can you hear me?
It needs presentation mode.
Yeah. Give me a second. Okay, is this in the presentation?
It's there, yeah. and we can hear you. Go ahead.
Great. Yeah, so I'm Jiahao Wang. So my today's topic is leveraging the large language model for improving the public transit system. And in this presentation, I will give you guys a brief exploration of the GPT models and other large language model and their state-of-the-art applications. So here is the outline of today's presentation. And to start with, what is the large language model? So the large language model is a type of a sophisticated AI model that can be used to understand, generate, and manipulate human languages. And the large language model is built on a specific deep learning model structure that's called transformer. And there are three elements that lead the success of the large language model. That is the huge number of parameters, the huge data set, and the training process, like including the pre-training and the fine-tuning process. And here is the performance of large language model here. As we can see, the dashed line is the human baseline, which means like in 2022, the performance of large language model on the area of natural language inferencing and the English language understanding has already surpassed the human's ability. And the bottom picture here is the picture of different large language models performance on different natural language processing tasks. And the model we chose here is GPT-3, which we can see it has a relatively balanced performance on different tasks. So let's move on to the state-of-the-art application of large language model. So the large language model in the transportation areas can be used for information extractions and formalization. It can extract information from some raw report written in natural language, and then by answering the questions from the user, it can give you a structured data. Like in this case, they can have a natural language written the crash report into a structured data has the time, location, and the situation inside. And also, you can also ask the large language model to generate code for the transportation analysis, such as you want to visualize some data in the data frame, and you specify that tasks and specify the language you want the GPT model to generate, and then boom, there's the code script, and you can use to make the visualization. And the next application here is you can use the large language model for some traditional transportation classification problem, such as the sentiment analysis. That you can analyze whether the user's feedback is positive and negative, and you can also use the large language model for binary classification, and also you can also use the large language model for multi-class classification, such as you want to determine what kind of situation the train has been delayed. Maybe it's because of the transit signal or some other situations, so they can do all those classifications. And the last applications here is the cross-modal large language model applications. So the cross-modal large language model application, it gives the ability for the large language model not only answer your questions based on some natural language input, it can answer you questions based on some other type of input, such as image input or some audio inputs, and give you answers based on those input resources. So we want to stress that the application of using large language model in this area is mostly problem-driven application. That means the answers you get or the results you get from the large language model is highly related to the questions you ask. The qualities and how you ask these questions will highly relate to the quality of the answer you will get. And the limitation is also quite obvious of the state-of-art applications. So the application right now is all function-oriented. Most of those are function-oriented applications. That means they just show you like this function can be done by large language model, but it's not integrated into a specific application scenarios. And all those applications is a one-way communication and a simple Q&A application. That means the GPT model gets the inputs and answer the questions based on answer the question from you and give out the answers. There's no interaction between the input source and also between the data source. And as we said, there's only input query being used as the data resource, like the GPT model based give answers on. So these are only simple single source application. There's no professional knowledge being used, and there's no real-time information is used. So our attempts of the application in this field is try to address those limitations. So in here, we put a scenario that we want to use large language model for better customer experience to give real-time answers and the customized answers based on the user's query. So there will be 3 applications, and those applications are pretty early stage, but they can gives us a idea of how those large language model can be used. So there will be twist writer, the trip advisor, and also the policy navigator. So before we start, I just want to give you guys a general overview of the approach we have used. So here we take the large language model as a vehicle, and it can be used as to transfer the information between the user side and the data side, which on one side is unstructured data, and on the other side is structured data. But the large language model itself cannot do this work by its own. So we have to give the large language model some other tools to use. So the first one is the prompt engineering, which can be seen as a roadmap. It can guide the large language model to transfer in the right way and to get some high quality answers. And the next tool is the computer engineering. That is something we provide the large language model the access for the large language model to access the transit data or some other structured data. And the last element we think is also very important for the large language model used for transit application is the human supervisor to make sure the answers from the large language model is reasonable and has been secured. So let's take a look at the first application. It's the twist writer. The twist writer application is taking the real-time service alert and station alert which can be directly gathered from the transit system. On the right-hand side is the system alert. I directly take a screenshot from the Go Transit website, and it can also take simple system alert, a system alert log info that has less information there. There may be no OD information instead of just a trip ID, and there's no some other suggestions. There's only like what status of those vehicles. And for the output of the twist writer, it will give you some twist in specific format, and you can also ask a twist to generate more like a human or like an influencer in Twitter. So let's take a look at the simple examples here. So after a system alert has been generated, there's only trip ID and the status of that alert of that vehicle and some situation descriptions. So after the GPT model or the twist writer get those informations, they will check whether this information is too hard for the passenger or for the user to understand. So the GPT model or the twist writer will automatically transfer the trip ID to a OD information matrix and also the departure and arriving time of that trip by interacting with the database has the trip information. And also if the twist writer think the status of the trip has been delayed for a really long time or stopped, it can search for the next trip information dataset to see whether there's available alternative trips for that trip. So after gathering all those informations, the twist writer can write something in a specific format, or you can ask the writer to give you a more natural tweets. So the next application here is the trip advisor. So the trip advisor is working by its input is the information by interact with the users, while the assistant is interacting with the user, it can gather information such as the OD information, the time, and the special needs from the user, and then it can output some customized trip suggestions and the customized trip alerts. So on the right hand is an example of the returned information from a assistant that it has some simple information about the trip and where it's from and where it had to, and some alerts from on the origin station and the destination station, and based on the user special needs. In this case, the user is carrying a bicycle with him on the GO train, so it has some information about the accessible buses and some low floor and ramps for ED boarding, and it can also provide you with the raw information that is directly from the database. So take a look of how this trip advisor is working. So when the user says, I want to go to U of T, the assistant will inspect this sentence and it realizes there's no origin of this trip. So it just asks you to provide a starting point of your trip. So I just say Oshawa, and then the assistant, sensing there's no specific start time of the trip, so they ask me to give the start time of the trip, and then the assistant thinks there's enough information here, and then they summarize those trip informations for me, and to ask whether I have some other needs, have some special needs they can assist with. So I said, oh, I have a bike with me. So they just so the assistant will keep thinking whether you want to continue this conversation, or there's enough information you provide and you want the assistant to do the search. So all those logic is happening autonomous by the assistant itself. So when the assistant, since there's no information you want to provide, they just stop asking for more information and just process the searching to give you some trip information, as we demonstrated in the last slides. So the last application here is the policy navigator. So there's already a policy navigator in the Go Transit website. Let's take a look of how this works. So imagine we have a question about how can I take a bike on the Go train. So what I have to do is in the interface, I have to select one choices from 10 options, to find one that is most related to my question. In this case, it's the Go service, and then the Go service will lead me to a second level choices. There's a lot of questions. I have to find one that is most related to my question, which is, can I bring a bicycle on a Go train or bus? And then if I click that option, it will return me a bunch of policies. And it's not customized, and there's a lot of words to read. And another situation is if I want directly ask the virtual assistant in the Go Transit website, the assistant will return me with nothing because it's not written in their system. This is just a if-else code, so there's no preset station, so he cannot directly answer you with these questions. So it acts more like a navigation bar instead of a assistant here. So to address this problem, we provide a policy navigator using the large language model, which can take the user query in a neutral language way, and we can output some customized policy advice based on the user query. So let's take a look at the examples here. So I'm here I'm asking the same question. Can I bring a bike with me on the Go train, which is not something like written in the system? So the assistant, the policy navigator, can directly answer me with information that I can bring the bike on the Go train, except there's some rush hour and a certain time at the Union Station, you cannot bring the bike. And the assistant can also provide you with the original policy that he makes a set suggestions based on. And if I change the questions I asked, that can I bring 2 bikes with me on the Go train, then the assistant will answer you no, because they're only allowed 1 bike on board on the Go train. But if I ask another question that can I bring 2 bikes on the Go bus, it's not the Go train, it's instead of the Go bus, then they will answer me with yes, because they're slightly different between the policy on the Go bus and the Go train that they allows you to bring 2 bikes on the Go bus. So while doing the application by using the large language model, even though the large language model is really promising on some functions, but we also find there's a lot of limitation of the large language model itself. So to start with, the first thing is that they did not know a lot of stuff. They did not know its logic knowledge boundary. It did not know what it's good at and what it's not good at, and it did not know whether the answer from it is right or wrong, and it did not know how to correct those answers. So all those limitations will lead to a bunch of serious problems, like it will generate some biased answers, and it will fabricate answers, and also it will have some reasoning errors there. And also those problems will lead to challenges like the first, which is really important, is the reliability of the applications, and also the professionalism of the application, how to evaluate the output from the large language model. And even though like using the large language model can give us a lot of flexibility and creativity, but it's at the cost of sacrificing the efficiency and the consistency of the applications. So to address those challenges, there are several best practices we have used to build up our application, such as for the reliability, we are using the prompt engineering, that there is a really famous idea of chain of thought, which can lead which improve the performance of large language model. And there's out-of-box tools, like, for example, there's launching and auto GPT that can help you to give a better prompts that lead the large language model. And for the professionalism of the large language model, there's a method called fine-tune. We can use a relatively less computing resource and less training data to train the model and encrypt the model to have some specific area knowledge and make suggestions accordingly. And the last one is the evaluation. So we can evaluate the answer from the large language model by using the higher version of GPT model to examine the similarity between the return answer from the large language model and also the target answers we have. And so I think during the practice, we think the most important thing is that we have to use the large language model as a tool which has no or limited intelligence. That means we have to we have to engage like regular autonomous checking or like human supervising while using the large language model. We have to limit the working place of the large language model in the application, which means we may need more coding on the logic sequence, but it will give us a more reliable answers from the application itself. So for the future work, there will be like 3 types of future works we can working on. Like first is the better customer service. We can build the chatbot we presented before, and then we can also build up a better automatic report system. Like we can ask the user to rate neutral language report other than fill up a really complicated form. And the last one is better transit control assistance system, which is really related to something we are doing right now and related to my research topic. So this application starts with the traffic situation embedding. And then after embed the traffic situation in a way that the large language model can understand, the large language model can be trained by using historical control records, the control strategies, the control handbooks, or some guidelines. And then the large language model is capable to make some control strategies based on those informations. And for our ongoing research. The phase 1 research is about the transit situation prediction, which takes the transit situation embedding as the really important steps in it. And for the phase 2 and phase 3 research, we will doing some research based on the human-involved reinforcement learning, which we want to train a deep learning model with human feedback that make the model perform some suggestions, not only aim for the not only aim for the optimal result, but also for something that is reasonable from a human perspective that it can be used in real life. So that is everything I want to present here, and thanks for listening. Yeah.
Thank you, Jiahao. It's quite incredible what's happened in the AI area, and it's really interesting to see some of the applications that could be in transit. Just to clarify, when Jiahao said traffic situation, it's really looking at transit bunching and gaps, and in terms of operational control and using these advanced prediction models. Our next speaker is Jilin Song. Jilin's a PhD candidate, and research focuses on transit operator planning and scheduling. Fun fact, he loves going on road trips, and his favorite road is California Highway 1 in Big Sur. It is an extraordinary, beautiful road. Okay, Jilin, it's all yours.
Okay, let me share my screen.
It's coming.
Can you all see the screen?
Need presentation mode. There we go. You're all set. All set.
Okay, thank you, Brendon. Hi, everyone. Today I'm going to give you an overview on Extraboard operator planning and scheduling. So let's start with the background. Operator planning falls under workforce management aspect of transit agency operations. It is a very important component for transit agencies because over half of all transit operating cost is in labor compensation. And also transit workforce shortage right now is a very hot topic around the world. One reason is that being a transit operator is a very stressful job. The transit operator needs to operate a very expensive vehicle every day while dealing with changing traffic conditions. Studies showed that transit operators have a much higher rate of absence compared to other workers. So the nature of public transit is about providing exact service according to schedules that are known to transit users. So when an operator becomes absent, there's a risk that the service will be canceled. And this is very detrimental to both user satisfaction and their loyalty. So how do agencies protect themselves against unexpected absences? So the answer is they usually keep a roster of extraboard operators or backup drivers. And the term extraboard operators can also be called spareboard in Canada. But for this presentation, I will just use the term extraboard because it is more commonly referred to in the literature. So the focus of this research is on decisions regarding extraboard operators. So their role is to fill in for something called open work. Open work is unassigned service for whatever reason. But operator absence is usually the predominant reason for open work. At larger agencies, extraboard operators can make up a large portion of the total workforce, sometimes up to 20%. And they're usually full-time operators. So currently, most transit agencies rely on sort of ad hoc methods to generate decisions for the extraboard without using mathematical methods, etc. Even though a lot of agencies are starting to use scheduling software to make their normal schedules. Here are the four decision levels in Extraboard planning and scheduling. First, strategic is the highest level, and it's about the overall hiring decisions for the workforce. Tactical decision is about sizing the Extraboard by garage and by day. And it is decided every sign-up period. And this sign-up period can vary by length, can vary in length by agencies. It can be like 1 month, 2 months, or 3 months. And the operational level is our focus today. So it is about giving daily assignments to the available Extraboard operators. And decisions are made on the previous day of the day of operation. We'll talk in details in the next slide. And the last component is real time. Actually, the real time decision level is usually not mentioned in the literature, but I think it's worth including because unexpected absence can occur at any time during the day of operation. And dispatchers have to decide which Extraboard operators they want to use in the real time. So now let's look at the operational level. Let's kind of look at the decision timeline. So for example, if we want to make decisions for July 3rd, then the decisions have to be finalized on July 2nd. And we introduce a notion called a cutoff time. So in this case, it is 12 p.m. The cutoff time can vary, but I'll just use 12 p.m. for this presentation. So before 12 p.m., any absence revealed will be known as known in advance absence. So for example, if a driver says, I won't make it on July 3rd before 12 p.m., then what we can do is we get an Extraboard operator to cover their job exactly. Any absence revealed after 12 p.m. will be known as unexpected absence. And what we can do is we give the remaining Extraboard operators report times. So the report time is a time where they show up at the garage to wait for open work to occur. And the subset of Extraboard operators who are given report times are also known as standby operators. And they'll kind of be the main focus. So the main challenge with the operational level problem is that when we're making report times, we don't know exactly what standby operators will be doing on their day of operation. So this is very different from normal scheduling process. And this problem follows a two-stage structure. In the first stage, before any absence is revealed, we have to decide on the report times. And as unexpected absences are revealed on the day of operation, the recourse decisions are to dispatch the standby operators who have shown up to cover the open work. So to ensure efficient planning and scheduling decisions, there are really two key tasks involved. The first is prediction of operator absence. So to have good decisions regarding report times, it's very beneficial to have a prediction of how much unexpected absence there's going to be. And a good model can just inform us the scheduling decisions. And also a good prediction model can help the management better understand absenteeism behavior among the operators. And the second is the Extraboard's operating scheduling process itself. And this can be modeled as an optimization model. And the goal is to give report times such that we minimize the expected uncovered open work. So in the literature, the topic of operator absence has been mentioned, but a lot of studies only focus on one or two things about operators. So for example, like whether it's their health conditions or it's their like service details. So as a result, no unifying theory was formed. And also, these absence models are usually done without considering Extraboard scheduling. And as for the Extraboard operator scheduling aspect, this is relatively unexplored, especially at the operational level, which is not good because the Extraboard operator can make up a big portion of the workforce. And for the limited number of studies, they usually focus more on the optimization model and not modeling for the absent. So let's put the two tasks in a flowchart. So a very normal approach would be when we give data, we first predict our quantity of interest, which is the absence level. And then we have that absence level as an input to our optimization model. So the problem with this approach is that the prediction model is trained by minimizing the prediction error, while the optimization model is about minimizing a cost. So in this case, it's like minimizing cost of service cancellation. But we don't know like how the two errors can affect one another. So now we introduce a novel approach, which can be called integrated predict and optimize. So the idea is that we want to have the factors used for the prediction directly involved in the optimization task. So this kind of approach is very new. It has not been widely used in transportation context. And one very frequently cited framework is called predictive prescription. And I think it fits our fits the problem description of Extraboard scheduling. So here's an illustration of how it works. So for example, we have historical operation records from the past year. So for example, on January 9th, we have a list of open runs that happened due to operator absence. And for each record, we also have the contextual information. For example, we have operator information. We have the weather on that day. We know what day that is, and these are like factors that affect absence. So now we want to make decisions for a new workday. So we do have the context information for the new workday. So what we can do is we compare the new context to the context of previous records. So we can give the more similar records more weight when constructing our uncertain scenarios. And we feed the uncertain scenarios into the optimization model, which gives us a decision output. So therefore, the integrated method is a very data-driven solution framework. Luckily, we now live in a big data world, and I think it presents a good opportunity to apply this kind of integrated method to the transit industry. Ideally, we would like to partner with a public transit agency. So many agencies have now adopted the usage of scheduling software, such as Hastus or Trapeze, and these can both store very high quality transit data. And also the good thing about partnership with the public transit agency is that we can learn more about what their current practices are regarding the Extraboard. And also we can learn about what they want to achieve through a research project. And here's an overview of like what the ideal operation records would look like. So as we mentioned before, we want to have historical records of daily operations and where and when the open runs occur. And then also the shift information can provide the contextual background. So in summary, the Extraboard planning and scheduling problem is a very pressing topic that it has often been overlooked, both in practice and in the literature. And by the end of this research, we'd like to demonstrate the value of an integrated approach by efficiently utilizing the abundance of data that's available in the transit industry. And yeah, that's the end of my presentation, and thank you for listening.
Thank you, Jilin. Yes, this is a very hot topic, and it's one where there's been mostly transit agencies rely mostly on experience, and, rules of thumb, and so it's very interesting to get into a more analytical approach. Thank you very much. Our third speaker for this session is Kareem Othman. He's a PhD candidate. In his PhD thesis, Kareem is exploring and developing advanced real-time transit management strategies in urban arterials, leveraging connected vehicle technologies. This is an interesting fact. When he was young, he wanted to be a Formula One driver, but he became a transportation engineer instead. Just as well, it's safer and more socially beneficial. So Kareem, it's all yours.
Thank you so much, Brendon. Can you see my screen?
Yes, but it looks like we're seeing. Amber, do you see everything? I mean, I
see the notes, Kareem.
Yeah, we're seeing the notes. It's not just in presentation mode. There we go. There you go. Yeah, that's good. Thanks.
All right, thank you, Brendon. So in this presentation, I will talk about transit driver advisory system and the main benefits of having this system in our transits. So I will start quickly with a motivation, and it has been frequently reported in the literature that around 35 to 50% of the battery consumption is really consumed in accelerations only, and this is when we talk about electric buses. So when we talk about accelerations, we can say like in the stop and go events. So we can say that 35 to 50% of the energy is really consumed in the stop and go events. And usually buses are stopping at two main locations. The first one, buses is stopping for dwelling and for boarding and alighting, and for allowing passengers to board and alight. And the second one is a bus stopping at the intersection. So if you want to control the stop and go events, you have to control one of these two main stop and go events. But we cannot really deal with, or we cannot avoid any stopping for dwelling. But what we can deal with is stopping at the intersection. So our main objective in this study is to optimize the bus trajectory to minimize the number of stop and go events. And in other words, we are trying to avoid or minimize any intersection stops. And in turn, we are achieving better energy consumption. And a second objective that can be achieved from this strategy or from avoiding intersection stops is improving the level of comfort for transit use. So in order to do that, we have three main strategies. The first strategy is the driver advisory system. And in the driver advisory system, you advise the bus driver with the traveling speed and the dwell time to avoid any intersection stops. And we have two supporting strategies. The first one is the space priority, and I will focus mainly on exclusive bus lanes and dynamic bus lanes, and time priority, and I will talk about TSP. I just wanted to highlight that those are just supporting strategies, so I will briefly mention these two strategies, but the main focus of this presentation will be on the driver advisory system. Okay, so what is the driver advisory system? It's actually a system that allows the bus to arrive at the intersection when the signal is green, and this way you are trying to avoid any intersection stops. And it's based on connected vehicles technology or vehicle infrastructure technology, and it tries to reduce the instance of bus stops, which means lower energy consumption, higher level of comfort, and so on. So how does it work? It's kind of establishing communication between traffic signals and the buses. So what happens here is that you have traffic signal broadcasting signal timing information to the bus, and then our algorithm comes in place and really advise the bus driver to travel at a specific speed to avoid any intersection stop. And in our driver advisory system, we have two main components. First is GLOSA, and the second is GLODATA. And the GLOSA refers to green light optimal speed advisory, and the GLODATA is green light optimal dwell time So what really happens here is that we use glow data to advise the bus driver with the traveling speed, and we use glow data to advise the bus driver with the expected dwell time to avoid any intersection stop. And as I have mentioned, we are advising the bus driver with a specific speed. So we need to make sure that the advised speed can be achieved in real life. So in order to do that, we need to do some space priority. So in this study, we focus on two main space priority strategies. Firstly, we will test our driver advisory system with exclusive bus lanes, and those are the traditional exclusive bus lanes, a bus dedicated for the general for public transit. But you might end up in a situation where the bus lane is totally empty and you have a highly congested network. And the second one is dynamic bus lanes. And dynamic bus lanes are lanes that are accessible to cars when transit is not present. And just to make it clearer, we have our dynamic bus lanes here. So dynamic bus lanes give priority to transit for a specific distance ahead of the bus. And the general traffic is allowed to use the bus lane ahead of this clear distance and behind the bus. So what really happened here is that you give priority to transit, and in the same time, you allow the general traffic to utilize the entire capacity of the lane. And this technology is based, or this strategy is based on connected vehicles technology. So you have moved from a situation where you have to improve transit performance on the cost of traffic to a situation where you improve the conditions for both transit and traffic using dynamic bus lanes. And if you are interested in knowing more about dynamic bus lanes and how does it perform compared to exclusive bus lanes, we have a study that really focuses on comparing the two strategies and showing which strategy is better under certain conditions, under certain traffic demand conditions, and under certain transit frequency conditions. Okay, let's get to the driver advisory system and how does it work. And I will show it in a time distance diagram, time space diagram. And let's assume a condition where we have a bus entering two segments. We have segment 1 and we have segment 2. And we have our signal here. So if we have a bus entering segment 1, usually the bus driver is traveling in a speed that's between the minimum and the maximum speed. And for our case here, you have a high probability that the bus driver will be traveling and arriving at the intersection, hitting the red phase and stopping at the intersection, then traveling again. But if we use the driver advisory system, what happens really here is that we actually try or evaluate if the bus is traveling at the maximum speed, we evaluate the bus arrival time at the intersection. If the bus is arriving at the green phase, we are advising the bus driver to travel at this maximum speed. And this is what's happening in segment 1. And when the bus is clearing signal 1, it enters segment 2. So what really happens here, the algorithm is gonna try and evaluate the maximum speed, but traveling at the maximum speed means that the bus will have to stop at the intersection at the red phase. So what really happens is that the driver advisory system algorithm will keep iterating until you reach really the speed that allows the bus to clear the intersection without stopping. So what really happened here is that you achieve the speed that's very similar to traveling at the maximum speed, but you have avoided any intersection stop. And so far I have explained the speed advisory. What's happening if we have a bus stop halfway in our segment? So I will show it here in segment 1. If we have a bus stop halfway, and at some conditions you will have your maximum speed. If the bus is traveling at the maximum speed, the bus will arrive at your bus stop, then stop for dwelling, and then travel again, and it will have to stop at the intersection at the red phase. And even if you select the minimum speed, you will face the same issue. So any selected speed will end up in a situation where you really have to stop at the red phase. So what really happens here is that you are moving the intersection stop to a stop at the bus stop. So you are increasing, in other words, you are increasing the dwell time, and then by that you are increasing the dwell time, you are adding some additional dwell time to avoid the intersection stops. All right. So in our research here, we have tested 4 separate algorithms. Every algorithm is focused on a specific objective. Algorithm A1 is really focusing on selecting the maximum speed that allows the bus to arrive at the green phase. And this is the one I have explained in the previous 2 slides. And we have A2, A3, A4. And for example, A3 is focusing on selecting the bus speed that actually allows the bus to arrive at the green phase and improves the headway regularity. A4 is focusing on improving the energy consumption. But for the aim of today's presentation, I will mainly focus on showing the results for algorithm A1. So for our simulation case study, we have selected one of the RapidTO project, one of the RapidTO corridors, and in 2019, actually the TTC have identified 5 corridors for the implementation of exclusive bus lanes to give transit some space priority. And in terms of priority, Eglinton East was actually selected as the corridor with the highest level of priority, and exclusive bus lanes were really implemented in 2020. So we have selected Eglinton East as our simulation testbed to test our driver advisory system and how does it perform compared to do nothing. All right, let's look at the results. So we have tested, as I mentioned earlier, we have tested the driver advisory system under 2 space priority strategies, starting with exclusive bus lane and dynamic bus lane. And with exclusive bus lanes, you will see 2 conditions. The first is maximum, is assuming that the bus driver is always traveling at the maximum speed. And the second one is the driver advisory system. And the same for dynamic bus lanes. You have 2 conditions. The first one is the red bar here is showing the average bus speed if the bus driver is always traveling at the maximum traveling speed. And the second one is the driver advisory system. And we can see that across the exclusive bus lanes and dynamic bus lanes, the driver advisory system is achieving the same speed as traveling at the maximum speed with exclusive bus lanes and with dynamic bus lanes. But when we talk about the stop density, which is the number of stops per kilometers, we will see that the driver advisory system is really achieving way lower stop density as a result of the reduction in the intersection stops. It's around 40 to 42% reduction in the stop density. And this reduction in the stop density can be translated into energy savings, around 10 to 12% improvement or reduction in the energy consumption. So what we have done really here is that we have achieved the same speed as traveling at the maximum speed. We have achieved a lower stop density, which means higher level of comfort, and in turn, lower energy consumption. And finally, for the time priority, I have mentioned that we will test it with transit signal priority, and it's only for the case of dynamic bus lane. And I'm gonna quickly show why have we tested it with the case of dynamic bus lanes. So if you have a bus that's arriving at the intersection at the beginning of the green phase, what really happens is that with dynamic bus lanes, you have some traffic really blocking or queuing at the bus lane. So you have really to take into consideration the traffic queuing in this lane. So you don't really advise the bus driver to arrive exactly at the beginning of the green phase, but you advise the bus driver to really arrive at the intersection exactly after the queue is clear. So you will keep iterating until you reach a speed that allows the bus to arrive at the intersection after the traffic queuing in the bus lane have really dispatched. So what really happens here is that you have some time lost to allow the traffic to really clear the bus lane. So to offset this time, we use unconditional red truncation, and we just to offset the traffic accumulating in the bus lane during the red phase. And just quickly, we have tested this strategy with 3 levels of transit signal priority. We assume 5 seconds red truncation, 10 seconds, and 20 seconds red truncation. And we will see that here we have some improvement in the average bus speeds. And when we compare the bus range, or in other words, we can say the energy consumption, we will see that across the different TSP levels, we have the same bus range, which means that you have the same energy consumption rate. So what really happens here is that you have higher speed, higher transit speed, which consumes more energy, but in the same time, you have lower stop density, which means lower energy consumption. So you have a balanced situation where the increase in the energy as a result of the bus speed will balance the decrease in the energy consumption as a result of the decrease in the number of stops. So just as a conclusion, we have seen the benefits of the driver advisory system. This system can really achieve the maximum traveling speed, and in the same time, you will have 40 to 42% reduction in the total number of bus stops, which can be translated into 40 to 50% higher level of comfort and 10 to 12% lower energy consumption rates. And I have mentioned that we have not really tested one scenario, one driver advisory system. We have tested 4. So the driver advisory system can really be used for achieving other objectives. For example, when we have tested it to achieve or to improve the headway regularity, we have seen that the driver advisory system can improve the level of service the regularity level of service from level of service E or F to level of service C. And when we have used it exclusively to improve or minimize the energy consumption, we have seen that the driver advisory system can achieve 20% reduction in the energy consumption rate. And with that, that concludes my presentation.
Thank you, Kareem. Very interesting. It's sort of the equivalent of dynamic speed controls that are all across Europe, but this is requires much more sophistication because it requires a connected vehicle linkage to the traffic controller. Just perhaps getting to questions. Let me see. There are some questions. Okay, I'll come back to that one. Kareem, question I had. You talked about red truncation. You tested red truncation. That's not a strategy that traffic engineers really like very much. They tend to use green extension more. Would there be a difference, or just any thoughts about the difference between the two?
Yeah, so we really have used the red truncation to kind of offset what's happening. So what's really happened is that when the traffic signal turns green, you have some traffic queuing in the bus lane. It takes time to dispatch this queue. So we are using the red truncation to kind of offset this traffic clearing time. But so like if we use the green extension, it's not gonna.
It doesn't help, yeah. And this is traffic turning right in the bus lane, but turning right and being queued, or because they're pedestrians or whatever. Yeah.
And actually, we are testing this strategy. We are currently testing it with an RL TSP, and this TSP is not considering just the transit; it's considering both transit and traffic. So we are gonna consider traffic really using RL Pro.
Good. Okay. Got a question for Jilin. Are you there? Yeah, unmute. Question. I was intrigued by your saying that the objective with the integrated prediction and optimization was to minimize decision error. How do you measure decision error? I was sort of curious about that.
Yeah, decision error would be like, so like there would be like a perfect decision if you knew what the uncertainty would be ahead of time.
But you haven't gotten into that. You have to define the metrics of what a perfect decision is.
Right. Yeah, like perfect decision would be like if you knew what the uncertain parameter was, like before it was even reviewed, then you would make that decision. And then it's really to compare like your prescribed decision versus the perfect decision. Like the performance discrepancy between those would be the decision error.
And it would require a lot of data, because a lot of the concept works because you're able to mine a very large number of observations and decisions, and then use it for both prediction and optimization. Is that correct?
Yeah, that's correct. Yeah.
Okay, good. I see a question. Let me just look for Jiahao. So Jiahao, how concerned should we be about feeding internal and potentially sensitive data to an LLM like ChatGPT? Are there any best practices that you recommend?
Okay, so for this question, like actually, when you input some messages to the GPT model, or for the ChatGPT or any other large language model, it's not using that GPT and using that information to train the GPT model. So technically, there's no data leakage for that situation. There's a news like talking about the ChatGPT data leakage is because of the website server. It's not because of the large language model itself. So, but if we want to avoid that data leakage because of the online service, we can deploy a offline large language model on our own server, or like on our own PC. But one serious problem is really related to this question is when we train the model, like when we pre-training the model using some sensitive data that has some user information inside, we have to be really clear, because when you're training the model with that data, the model will memorize those informations. So the best practice right now is using such as you can encode those input data into some secure way, and also you have to add some human supervisor, or you have to write some code to automatically checking whether they have, for example, if in the training data you have some user names there, you have to write a code can automatically find whether the output from the large language model has username patterns inside, and then you have to delete or mark those parts information out of the return value from the large language model.
Yeah,
so that is currently concerned.
So basically to isolate it and prevent it from being used per se.
Yeah. But if you just using the large language model but not training, there's no I think there's no concern about the data leakage if you use as a offline service there.
Right, but don't they have to be trained automatic? I mean, to even
no, the logic of ChatGPT, they said on their website, they are not using the user's input as their training data. They just use the data before 2021. Yeah. So the new data is not used to training the data, training the model. Yeah.
That's interesting.
Yeah.
I think those were all questions from the previous session. Does anybody else have any other questions they would like to ask? Yeah, Jilin, in terms of the decisions, you mentioned the report times. I mean, it's sort of setting this threshold, and then what the report times would be, that would be a key decision, correct? Did I understand that correctly?
So what do you mean by?
Well, it will be the size of this Extraboard is one decision, but the report time for the unplanned, to cover the unplanned absences would be another key decision, right?
Yeah, that's right. Yeah, because the sizing was done in a higher decision level. It's basically a known quantity on the day of operation. So we're just assuming that, we're dealing with
that's assumed.
size.
Yeah. And there's also I mean, as part of the Extraboard, there's also drivers that are positioned in the field with standby buses and so forth. That's part of the equation too, right?
Yeah, I mean, there are a lot of different factors in this problem. Different agencies may have different uses for Extraboard drivers. So it gets very complicated when you consider all the factors. But there are many different complications or small nuances.
Right. Question for Kareem. The bus acceleration optimizations are super cool to hear. In the dynamic lanes, was there a consideration made for traffic behind the bus as it attempts to make the lights? I don't know if I'm misunderstanding, so feel free to correct me. Well, I guess the question is, you're not accelerating buses. Most of the actions are to slow the buses down, right?
Yeah, exactly.
It sounds like the question is, if you were actually trying to accelerate the bus, then cars might tailgate to take the benefits. I mean, sometimes this happens with TSP as well. I mean, they tailgate to get through because they know the bus is going to get priority. But most of the actions you were discussing, if I remember correctly, were either to slow the bus down or to hold it at the dwell to increase the dwell time by just holding it and with doors open at the stop or things like that, right?
Yeah, exactly. Yeah. We cannot exceed the maximum speed. We have a range between the minimum and maximum speed.
That's a given. Yeah. Okay, well, I'd like to thank all three of you. Thank you very much.